Good day everyone. In this series of videos we will discuss the time response of both first order and second order systems. We will also discuss how the S-plane maps into the Z-plane. And by using the correlation between the regions and the two planes, we will show how the transient response depends on the poles in the Z-domain. We will also show the effects of the system transfer function on steady state error. And MATLAB will be used on some occasions to show the details of the above. But first we will consider a simple model for a first order system, and then we will discuss all the points highlighted here. And then in another series of videos we will repeat with the second order example model. But for now we will start with the first order model. For the first order example, let's assume we have a tank of water that we wish to control the water level and has some means of water inflow via a horizontal pipe and some sort of outflow. So we'll assume that the water inflow on the left hand side, and what we would like to control is the level of water in the tank. So here we have some sort of volumetric flow rate coming in and some sort of volumetric flow rate out. And perhaps we can express the height of the tank as h. So we need to find a relation between the input to the system, which is the volumetric flow in, and the output, which is the water level, represented as h. Now the volumetric flow rate, or the flow in, has a unit of meter cube per second. And the water level is a meter. From the thermodynamics knowledge, you are perhaps familiar with many conservation laws, such as the law of conservation of mass, conservation of energy, and conservation of momentum. These are sometimes called balance equations. For this example, it is very convenient to use the conservation of mass to find the relation between the input and the output. The conservation of mass law is one of the fundamental principles in nature. It simply can be expressed as mass in minus mass out equal to the net change in mass for a controlled volume or open system, which is this case. The conservation of mass can also be expressed in rate form as mass rate coming into the system minus the mass rate leaving equals to the rate of change of mass within the control volume of the system. These equations are often referred to as the mass balance and are generally applicable to any control volume undergoing any kind of a process. Mind that the unit for the first equation is simply in kilograms, and the unit for the second equation is in kilograms per second. The mass and volume flow rates are related by this relation. Mass rate equals to the density multiplied by the volumetric flow rate. So this has a unit of kilograms per second. The density is mass over volume, and the volumetric flow rate is meter cube per second. Of course, the mass rate can be expressed also in terms of the liquid velocity. So the mass rate equals to the density multiplied by the average velocity of the liquid multiplied by the cross-sectional area. But this equation will not be used in this model. So the conservation of mass really tells us that if the inlet mass is equal to the outlet mass, then the net change of the control volume or the tank mass is equal to 0. And in this case, if there's no change in the mass within the tank, then H will be the same. The conservation of mass relation can be simplified even further when the fluid is incompressible, which is usually the case for liquids. So if we substitute the mass rate relation with the volumetric flow rate in the conservation of mass law, we get the density, assuming this is water, so that will be the density of water minus the flow leaving, density of water leaving, multiplied by the volumetric flow rate, equals to the density of the volume change rate. And since the density is the same, so we can divide by the density. You recall from the fluid mechanics knowledge that the volume flow rate for laminar flow through a horizontal pipe of diameter d and length L can be expressed as volumetric flow rate equals to change in pressure phi diameter of your pipe, or hydraulic diameter if it's not a circular pipe, divided by 128 times the length of the pipe multiplied by the viscosity. This equation is known as the Poiseuille law. And remember, this equation is valid for laminar flow and horizontal pipe only. If the pipe is not horizontal, you have to include another term which includes the gravity effect. And this flow is called the Hagen-Poiseuille flow, in honor to the work of Hagen and Poiseuille on the subject. So mainly if you are using a pump to deliver the pressure difference, you can see that the pumping power is proportional to the length of the pipe and the viscosity of the fluid. And it's inversely proportional to the fourth power of the diameter. Therefore, the pumping power requirement for piping system can be reduced by a factor of 16 by simply doubling the pipe diameter. The main reason the Poiseuille law is mentioned here is just to show that the volumetric flow rate is directly related to the pressure. So one way to control a flow rate by an engineer to the tank shown here is by adjusting the pressure. And if you have as well a static pressure head, in this case, this will dictate the flow output of your system. And to make sure you are in the laminar flow before you use this equation, you have to calculate what we call the Reynolds number. And Reynolds number is dependent on the density, the velocity of your liquid, the diameter of the circular pipe or hydraulic diameter in case of non-circular pipes, divided by the viscosity. Once you calculate the Reynolds number, you will be able to tell if you are in the laminar flow or not. If you recall the Reynolds number from fluid mechanics, if you obtain a Reynolds number which is less than or just equal to 2300, then you are in the laminar flow. If your Reynolds number is somehow between the laminar and the turbulent, this is what we call the transitional flow. And if your Reynolds number is greater than 4000, then this is what we call turbulent flow, and different set of equations are used in this case. As mentioned before, we are assuming here that the flow is laminar throughout, and the pipes are horizontal and circular. Please remember, as well from fluid mechanics knowledge, the pressure exerted by a liquid can be expressed as rho GH. So for example, the pressure at this point is the same as the pressure at this point, which is equal to the density of the liquid multiplied by the gravitational acceleration multiplied by the height of the water on top, where the rho is the density of the liquid and h is the height. If we apply the Poiseuille law, then the volumetric flow rate out can be expressed as simply a rho GH. However, because we have other terms included in the equation here, if we assume this is some sort of constant, and manipulating this constant, we can write it somewhere here as K, for example, pressure outlet. So we denote now a constant K to represent all of the terms other than the pressure difference and the volume flow rate. Or perhaps maybe we can just call it P out. PO. So this is our first equation. Also, the volumetric flow rate coming to the system is as a result of a pressure difference according to the Poiseuille law. So if we assume that there is a pressure which is higher than the inlet pressure, then that pressure difference is what causing the flow rate to happen. And as we done before, if we assume the other coefficients are presented as Kb high in this case, so we obtain a second equation. Now, substituting equation number 1 and 2 in the conservation of mass law here, we get the following. And the volume here can be expressed as the area is constant, is not changing, and the changing parameter here is the h. Since our desired input is the volume flow rate and the desired water level output is the h, then we can write this equation as If you are interested, however, in the control of pressure in as the input, then perhaps you could substitute the equivalence of the volume flow rate coming into the tank in terms of Pn and rho gh, and you can combine the h parameters together, and then you can form up your first order differential equation. And Pn, or the pressure required at the input, should be greater than the pressure at the tank inlet. If Pn is greater than rho gh, then in this case you will have a flow rate coming into the tank. Now this equation can be written as the general first order format where the input is on the right hand side and the output we desire to control on the left hand side. Remember, if the coefficient is made 1, then what is left here will be your time constant, if you remember. So we can rewrite this equation as so to make this term equals to 1, we could divide by rho g and multiply by kpo. If we do this for the differential equations, we get the area multiplied by kp constant divided by rho g. For convenience, if we assume the first coefficient 0.5 and this one as, and applying Laplace to this differential equation, we get then the transfer function in the S domain equals to the output, which is the hs over the input, vs over dot. This is the first order transfer function for the water level control tank system that we will be using in the coming lectures. We will be analyzing the time response for both the S continuous domain and the Z discrete domain as well. A cross comparison will be carried out. The effect of the sampling time will be discussed. MATLAB will be used for simulation for cross comparison.